Welcome to QubitInk. In this video, we begin the mathematical language of quantum mechanics, vectors, Dirac notation, operators, inner products, tensor products, and functions of operators. In the previous video, we focused on quantum algorithms. We saw reversible logic, oracles, phase kickback, and interference working together to process quantum information. This expression captures the pattern we used repeatedly: prepare a superposition, apply an oracle, and encode information into relative phase so that interference can reveal useful structure. Now we slow down and look underneath those algorithms. To understand why quantum states and gates behave the way they do, we need the mathematical language that describes them. That language is finite-dimensional complex linear algebra, written in the compact notation used by quantum mechanics, called Dirac notation. The ideas in this video form a chain. We start with vectors and inner products, move to operators, then combine systems with tensor products, preparing the language needed for the quantum postulates. This order is not arbitrary. Quantum states are vectors, physical transformations are operators, and composite quantum systems live in tensor product spaces. So our goal here is mathematical preparation. Once these objects are familiar, the physical postulates of quantum mechanics become much easier to state and interpret. The roadmap has two parts. First, we build the basic linear algebra language and operator notation. Then we study Cauchy Schwarz, eigenvalues, adjoints, tensor products, and operator functions. A quantum state is a vector. A basis gives it coordinates. Ket E1 and ket E2 define the basis. Ket V is the vector we want to describe. The dashed lines show its two components, V1 and V2. Those same components give both the column form and the expansion in the chosen basis. For a qubit, ket 0 and ket 1 form the standard basis. A general state uses amplitudes alpha and beta, whose squared magnitudes sum to 1. We can also choose ket plus and ket minus. The vector space stays the same, only the basis description changes. A ket is a vector. A basis gives its coordinates. We begin with a vector space. It is a collection of vectors for which vector addition and multiplication by scalars are defined, and both operations keep us inside the same space. The equations show those two closure properties. In quantum mechanics, the scalars are generally complex numbers, so complex vector spaces are the natural setting. The space C to the n contains ordered lists of n complex numbers. After choosing a basis, those numbers become the coordinates of a vector. Here ket V is represented as a column with entries z1 through zn. Each zj is complex, and the column is simply the coordinate form of the vector. For a single qubit, n equals 2. So a qubit state belongs to a two-dimensional complex vector space and needs two complex coordinates. Using the computational basis, those coordinates are written alpha and beta, giving ket psi equals alpha ket 0 plus beta ket 1. A linear combination builds a new vector by multiplying several vectors by scalar coefficients and then adding the results. The coefficients of 1 through am determine how strongly each vector contributes to the combination. The span is the set of every vector that can be produced by allowing those coefficients to vary over all permitted values. This notation denotes the span of the listed vectors. If that span equals the whole vector space, the vectors are sufficient to generate every vector in it. A basis is a linearly independent set that spans the entire space. Once a basis is chosen, every vector has a unique expansion in terms of the basis vectors. The number of basis vectors is the dimension. In quantum computation, the computational basis is especially useful because its basis labels correspond naturally to classical bit strings. Now we move from vectors to operators. An operator is a rule that acts on vectors. Once a basis is chosen, that rule is represented by a matrix. Here the vector ket V is transformed by the matrix A. The basis directions also move, and the vector follows the same linear rule. This is the geometric meaning of matrix action. Linearity means sums and scalar multiples are preserved. Applying A to a combination is the same as applying A to each part. Then a second operator, B, is applied. The expression B a ket V means first apply A, then apply B. Matrix products represent actions performed in sequence. With that geometric picture in mind, let us write the same idea formally. In quantum mechanics, a state vector is written as a ket, such as ket psi. Once a basis is chosen, the state can be written either as a coordinate column or as a linear combination of basis kets. These are equivalent descriptions. The important point is that the representation depends on the basis, but the underlying state vector is the same mathematical object. For one qubit, ket 0 and ket 1 form the computational basis. Ket plus and ket minus form another orthonormal basis of the same two-dimensional space. A ket is represented as a column vector. The associated bra is obtained by complex conjugating each component and then transposing the column into a row. The star denotes complex conjugation, while the dagger denotes conjugate transpose. In compact notation, bra V is ket V dagger. This table is a useful dictionary for Dirac notation. Kets are vectors, bras are conjugate transpose row vectors, bra ket expressions are inner products, and ket bra expressions are operators. The notation may look unusual at first, but every entry in this table is ordinary linear algebra written in a compact language adapted to quantum mechanics. The inner product of V and W is a complex number that measures their overlap. The norm of a vector comes from its inner product with itself. A valid quantum state is normalized, so bra psi ket psi equals 1. An outer product is different from an inner product. Ket V bra W is an operator. When it acts on ket X, it returns ket V multiplied by the overlap between W and X. A particularly important outer product is ket psi bra psi. It is a rank 1 projector, and applying the same projector twice has the same effect as applying it once. Now suppose the vectors Ej form an orthonormal basis. Each basis vector defines a projector onto its own direction. Adding all of those basis projectors gives the identity operator. This is the completeness relation, also called the resolution of the identity. This identity is used constantly because it lets us insert a complete basis when expanding states, operators, and probability amplitudes. A linear operator maps vectors to vectors while preserving linear combinations. The equation makes linearity explicit. Applying A to a weighted sum is the same as applying A to each vector separately and keeping the same coefficients. Quantum gates are linear operators, and physical gates are unitary. Once we know how an operator acts on a basis, linearity determines its action on every vector in the space. After choosing a basis, every finite-dimensional linear operator can be represented by a matrix. The coefficients Aij tell us how A acting on basis vector Ej decomposes along the output basis. Equivalently, Aij is the matrix element bra Eia ket Ej. This gives a useful interpretation of a matrix. Its JTH column records exactly where the operator sends the JTH basis vector. Operator multiplication represents sequential action. In B a ket V, A acts first and B acts on the result. The identity operator does nothing and leaves every vector unchanged. Order matters. Matrix multiplication is generally not commutative, so AB and BA can describe different transformations. The identity together with X, Y, and Z gives the standard Pauli family. These matrices are fundamental single qubit operators and appear throughout quantum computing. It is worth becoming familiar with both their matrix forms and their actions, because the Pauli operators reappear in gates, observables, rotations, and error models. Their action on the computational basis is simple. X exchanges ket 0 and ket 1. Z changes the phase of ket 1. Y combines a basis flip with complex phases. Each Pauli matrix is both Hermitian and unitary, and squaring any Pauli operator gives the identity. The computational basis is orthonormal. Each basis vector has inner product 1 with itself, while ket 0 and ket 1 have 0 inner product with each other. An inner product of 0 means orthogonality. An inner product of 1 with itself means the vector is normalized. The compact expression bra I ket ej equals delta ij summarizes both facts. It is 1 when the labels match and 0 when they do not. The Cauchy-Schwarz inequality places a fundamental bound on the overlap between two vectors. Their overlap cannot exceed what is allowed by their lengths. Mathematically, the squared magnitude of the inner product is at most the product of the two self-inner products. If both vectors are normalized, each self-inner product equals 1, so the magnitude of their overlap can never exceed 1. In ordinary real geometry, a dot product contains the factor cosine theta. Cauchy-Schwarz is the corresponding Hilbert space bound. Equality occurs when the two vectors are linearly dependent. The Cauchy-Schwarz inequality is about overlap. The inner product tells us how much one vector points along another. Here, ket v is projected onto the direction of ket w. This orange projection is the part of ket v that overlaps with ket w. The projection can be small, but it cannot be larger than the length of the vector itself. That is the geometric content of the inequality. For normalized quantum states, both lengths are 1, so the absolute value of the inner product is at most 1. In the orthogonal case, the projection disappears. The overlap is 0. Orthogonal quantum states are perfectly distinguishable. An eigenvector is a special direction for an operator. When the operator acts, that vector is not rotated into a different direction. Instead, the operator only rescales it. The equation A ket v equals lambda ket v expresses this condition, with ket v required to be non-zero. Ket v is the eigenvector, and lambda is its eigenvalue. The eigenvalue tells us how that special direction is scaled. Pauli z gives a simple example. Ket 0 is an eigenvector with eigenvalue +1, while ket 1 is an eigenvector with eigenvalue -1. If an operator has a complete basis of eigenvectors, we can choose that eigenbasis as our coordinate system. In that basis, the operator becomes diagonal. The spectral form writes the operator as a sum of eigenvalues multiplied by projectors onto the corresponding eigenvectors. This representation is especially useful for Hermitian operators and will later make functions of operators very easy to define. Eigenvectors are special directions of an operator. In this animation, a general vector changes direction when the operator A is applied. But the eigenvector stays on the same line. It may stretch, shrink, or flip sign, but its direction is preserved. This is why we write a ket E equals lambda ket E. The number lambda is the eigenvalue. It tells us how the eigenvector is scaled. Then we see the Pauli z example. Ket 0 is unchanged, while ket 1 gains a minus sign. So ket 0 and ket 1 are eigenvectors of z. Eigenvectors reveal the natural directions of an operator. The adjoint of an operator A is written a dagger. For a matrix, the adjoint is the complex conjugate transpose. In matrix notation, we can write a dagger as the transpose of a star. The defining relation shows how the adjoint moves an operator from one side of an inner product to the other. This relation is central to quantum operator algebra. An operator is Hermitian, or self-adjoint, when it is equal to its own adjoint. So the defining condition is simply a dagger equals A. Hermitian operators have real eigenvalues, which is why observables are represented by Hermitian operators. Projectors are an important example. A unitary operator satisfies U dagger U equals the identity. Quantum gates are unitary before measurement. This equation shows the key consequence: applying the same unitary to two vectors leaves their inner product unchanged. Therefore unitary transformations preserve lengths, relative angles, and normalization. In quantum mechanics, that means total probability is preserved. Tensor products provide the mathematical rule for combining separate quantum systems into one larger system. A product state ket A tensor ket B is often written more compactly as ket A ket B. Both notations describe the same state. At the level of vector spaces, the combined state belongs to the tensor product of the two individual Hilbert spaces. Dimensions multiply under the tensor product. Two qubits each have dimension 2, so together they form a four-dimensional state space. The computational basis of 2 qubits therefore contains 4 states, ket 00, ket 01, ket 10, and ket 11. Each 2-qubit label is shorthand for a tensor product. For example, ket 0 tensor ket 1 becomes the 4-component column shown on the right. Operators combine by tensor product as well. If A acts on the first system and B acts on the second, their joint action is represented by a tensor B. The equation shows that the joint operator acts on the corresponding parts independently. A acts on ket V, while B acts on ket W. For example, X tensor I flips the first qubit and leaves the second qubit unchanged. Now we combine quantum systems using the tensor product. A single qubit has 2 basis states, ket 0 and ket 1. If we have 2 separate qubits, system A and system B each have dimension 2. The joint system has dimension 2 times 2, which is 4. Its basis states are ket 00, ket 01, ket 10, and ket 11. A general 2-qubit state is a superposition of all 4 joint basis states. Each basis state has its own complex amplitude, and the squared magnitudes add to 1. The key idea is that the basis grows multiplicatively. 2 qubits give 4 joint basis states. We can also define functions of operators. One approach uses a power series, just as we define functions of ordinary numbers. When the operator is diagonalized, the definition becomes especially simple. Apply the function to each eigenvalue and keep the corresponding eigenprojector. The operator exponential is particularly important because it appears in quantum time evolution. For a Hermitian Hamiltonian H, the exponential of -iht is unitary. The state at time t is obtained by applying this unitary time evolution operator to the initial state. This is where the linear algebra language connects directly to physical dynamics. For an operator p with p squared equal to the identity, the exponential reduces to a cosine term times the identity and a sine term times p. This form is especially useful for Pauli rotations. We can now see the full mathematical chain. Vectors describe states, inner products describe overlap, operators describe transformations, and tensor products describe composite systems. With these objects in place, the postulates of quantum mechanics become much easier to formulate and understand. State space, evolution, measurement, and composite systems will all be expressed using the same language developed in this video. The main ideas can now be summarized as Dirac notation, operators and matrices, inner products, spectral methods, and tensor products. Quantum mechanics is not built from a new kind of arithmetic. Its mathematical structure is complex linear algebra, used with precise physical rules. The next step is to turn this mathematical language into those rules, the postulates governing states, evolution, measurement, and composite systems. In the next video, we move from mathematics to the postulates of quantum mechanics, including state spaces, unitary evolution, measurement probabilities, and composite systems. At that point, the mathematical language we built here becomes physical law. The main reference for this video is Nielsen and Chuang, Quantum Computation and Quantum Information, Chapter 2, Section 2.1. Thank you for watching QubitInk. Quantum computing, one idea at a time.